Hello again and welcome. Today we're going to be looking at the Brymen BM869s. One of the questions that I see frequently is, what is the life of this meter? So to help answer that question, I set up some software along with a stepper motor, and I've been rotating the switch assembly on a few different meters. While I'm doing that, I've got an external meter that's measuring the switch contact resistance. So I'd like to do that same test with this meter. The problem with running this exact one is that I purchased this meter a little over 2 years ago, and it's basically the only handheld meter that I use. And because it's seen a couple of years of heavy use, I don't know how that would bias the test results. So what I'd like to do is get a brand new one. So I mentioned to Brymen that I was interested in running a test like this, and they offered to send us a brand new BM869s. So let's go ahead and have a look. I think what I'd like to do is take the two meters apart and see if there's any differences between the two. Now again, I purchased my meter from TME. They've probably added these additional stickers. You can see how this one's worn down. Let's just go ahead and pop the cover. You don't see any damage to the switch yet. You wouldn't expect that. Meter looks in very good condition. So it's shipped with a Toshiba brand battery. I don't remember what came with this one originally. Again, the two cases look identical. Of course, Busman, it looks like has changed their fuse logos over the years. You can see my connectors are a little more beat up, but we're really concerned about the revision of the two circuit boards. So we can see the markings on the mezzanine board are identical. These are both marked 2J06-20, 2G-1020. Let's go ahead and pop the two circuit boards. Looks like the shielding for the 2 meters is identical. You can see the color on the new circuit board is a little different. It's slightly darker pigments than the original one. So I asked Brymen about the difference in the color in the 2 circuit boards. They did respond saying, "We have never changed the PCB vendor or requested to change the plating. They should just come from different PCB production lots." So that would explain the difference in the coloring between the two. If you look at the switch on this, you can see it has contacts on the mezzanine board as well as on the base board. Let's go ahead and we'll disassemble it from the bottom. This is one of the wiper contacts that I would typically see in some of the cheaper meters I've looked at. You can see there's quite the difference between the two. So again, looking at the circuit board, there appears to be no signs of any lubrication. You can see that for the most part they chose not to put the vias right in the center of the pad. However, this one right here, it does look like the wiper could actually run right across that via there. You can see it's offset just slightly. The rest of them are far away from the center of the pad. That's by far the closest one. The other thing that you don't see with this meter again is they do not run any of the traces between the pads. Looking through the manual, there's a couple of things I was going to point out. The bar graph on these meters that I'm so impressed with, you can see these update at 60 times per second. These are some of the fastest meters that I've seen as far as the bar graph update rate. What I wanted to mention is that there's no IP rating for this meter. At least it's not called out inside the manual. The only thing they have in here is relative humidity, 80% for temperatures up to 31 degrees C, decreasing linearly to 50% relative humidity at 45 degrees C. And then they give a storage temperature of -20 to 60 C with less than 80% relative humidity with the battery removed. That's the only thing that I see for it. There's no markings on the front of the meter that give any kind of an IP rating. But if we look at the meter itself, you can see these rubber O-rings located around the banana jacks. And you can also see the screws that hold the cover in. There's a rubber O-ring on each one of these. And if we look down inside of the channel, you can see there's a rubber O-ring that runs around this. Right, looking at the battery cover, Again, you can see this rubber O-ring around it. And then again, looking at the box itself, you don't see any mention of a IP rating. Again, I just thought that was kind of interesting that there's really no mention about the waterproofness or anything. But obviously they've considered that. So I wrote Brymen and I asked them if this BM869s actually did have an IP rating. And they responded with, "We submitted the BM869s to UL to test and got an IP54 approval." And then they provided me with a link to download the actual report. Then they went on to say, since the IP test would increase the production costs a lot, we do not want to test IP for every unit before shipment. That was the reason we did not specify an IP in the manual, spec, or catalog. Anyway, you can see I've got our wires attached. I'll go ahead and pop the cover on. And I assume our meter will power back up. Again, I'll test this without the battery installed. Yep, no problem at all. So I ran the wires up through the battery cover, and then I just kind of snugged these screws down a little bit. This should be just fine as far as holding those wires in place. Let's just have a look and see what the resistance is. Looks like about 0.2 ohms, 2.1 ohms. So when I was talking with Brymen about running this switch life cycle test, it turns out they actually do a test similar to this for all their designs. They sent me a few clips of their test jig in operation, and they've agreed to allow me to include those as part of this video. So I'm going to go ahead and do that. See, I have our stepper motor attached to our meter. Basically, I start by eyeballing the system. I want to make sure that nothing's going to be in a bind. Then I'll set the switch to the center position. So this is looking at the software that I'm using to life cycle the meters. Down here you can see I set the number of cycles for 50,000. And above that you can see we've selected 60 hours of runtime. Basically what I'm looking for is to cycle the switch at about 3 to 5 seconds. I could run these faster, but what I found is running it slower, it doesn't build up any heat in the switch assembly. So the first thing we're going to do is align the system. So what that's going to do is rotate the switch until we find the stall current of the motor, and then that's going to select the operating current as a percentage of that. The next thing it'll do is rotate the switch to find the two dead stops. Once it has that, we can go ahead and start the cycling. So let me just show you what that's like. And that's basically all there is to it. You can hear the software slowly increasing the speed of the motor, and that's because it's trying to determine how fast it needs to cycle this switch in order to complete the 50,000 cycles in the 60 hours. Currently we're at 1,000 cycles. Alright, so I now have about 4,000 cycles on this Brymen. Let's try to compare that against the old one. The meter now has about 18,000 cycles on it. I'm not noticing any difference as far as the sound. So I've just finished the 50,000 cycles. You can hear it clicks pretty good still. Again, the meter on the right is the one that I purchased originally, so this meter is a little over 2 years old. Let me just rotate the dial on both meters to give you an idea what the two sound like. I don't really see any problems here. Because this was a brand new meter, I think what I'd like to do before I tear this thing apart is just go ahead and put the battery back in, reassemble the meter, and let's just see if this switch is intermittent at all. Alright, let's just power it up. At least that seems to work. Let's try it in resistance mode. Let me get a couple of leads. Alright, so this will be a 1 ohm resistor and 50 ohms, 100 ohms. Let's try moving the knob just a little bit. And I'm pretty far off the center point. This would be 1 giga ohms. So it should be 1. Yep, it is. So it doesn't look like it's leaking at all. It should be the 5-volt mode, and that looks fine. Let's try it in AC volts. Again, this should be 2.5. Looks good. 60 hertz, that's correct. So it looks like the meter is still functional. I think what I'd like to do now is just go ahead and take this apart and let's have a look at the contacts. To me, it looks like the contacts have worn a little, but it's very difficult to tell. There's definitely some buildup right around the tips. And again, the circuit board looks pretty good. Looks like there's a little bit of buildup on it. Right there you can see that little bit of black. And there's some light dusting up in here. Maybe along here. I don't see any place where it looks like the plating is worn through and the copper is exposed. It's a little difficult to tell. Let's get out the microscope and we'll have a look at it. So this is looking at the rotary switch on the main board. You can see there's quite a bit of debris. I believe that this is all solder mask. The pads themselves look really good. Let's just zoom in a little bit. You can see in this area right here, it looks like it's starting to wear a groove into the circuit board. This is that pad. I was concerned that it may actually cut through the via, but it looks like it's nowhere near it. There's definitely some wear in the pads, but all in all, things look real good. At some point I may take and measure to see how deep these grooves really are. On some of the meters we've actually warmed down far enough where you could start to see copper coming through. And I don't see that with this board. Normally with those you'll see specks of metallic dust, and I'm certainly not seeing that. You can see where it started to erode just the lip of this pad. So we move towards the center of the switch, you can see a lot more debris. Alright, this is taking a look at the contacts themselves. It looks like there's just a little bit of debris. Yeah, just around the outside edge of it. All this here, I believe, is just buildup from the solder mask. Again, it doesn't look like there's any metallic flakes in any of that. None of these really look all that wore. Again, just some buildup around the tips, but all in all, they look pretty good. This is looking at the opposite side of the rotary switch. And again, it looks very similar. This side only has the two contacts. I noticed one of the contact wipers that are on the top side of the board, so this is one of two, had cracked. You could see the crack right here. So it's a nice clean break. Yeah, I would have no way to know how many cycles it went through before this actually fractured. With Brymen doing their own life cycle tests on their switches, I'm sure they're aware of this. Just looking at it from the side. This is looking at the break from the back side of the contact. I contacted Brymen about the cracked contact, and Brymen's response is that they've never seen that with their 30,000 life cycle tests. So it's very possible that the contact could have been damaged from the additional 20,000 cycles that I run. This is looking at the pads on the opposite side. See similar wearing. You can see a little bit of metallic dust right there. I think if I hit this thing with some cleaner and just wash these off, we'd get a better feel for how this thing is worn. So let me just get some Pro Clean out. This is looking at the two Q-tips I used to clean them. You can just see how black these are. They're basically like this all the way around. Again, I'm not really seeing any metallic particles in here. Again, you can kind of see as it's wore this groove down in the center, eventually the wiper starts wearing around that whole perimeter. This looks like copper again showing through. Just a little strip of it. And again, all in all, looks pretty decent. So this is looking inside of the switch for the BM869s. Here we can see the detents along with the spring. You can see there is no damage to this whatsoever. Actually, there's no signs of any wear. You can see it has a fairly long arc on here. These can be flexed a fair amount. Again, this is looking at the software that I use to life cycle the switches. If we go under post-processing, next we can go ahead and add all the data that we've collected so far. You can see I've changed this a little bit. I now have this slider switch on the side to select how we view the data. So this would be the normal raw data. And again, the vertical axis is in resistance from 0 to 1000 ohms. And then the number of cycles is in the horizontal axis. So if we select mean 50 samples, this is a rolling average of the last 50 samples. And accumulated is essentially just that. It's an accumulation of all the samples that we've taken. So you can imagine if the switch resistance was always 0 ohms, perfect. This would be a flat line going across the number of cycles at 0 ohms. So the resistance in this case is always going to be increasing. It'll never decrease. The blue trace on the top is the Centec 830 meter that I bought from Harbor Freight. This has the highest total resistance, and you can see it gets flat here where you would expect it to increase. And again, that's because I stopped cycling this meter at roughly 17,000 cycles, and that's basically where the switch had opened up. The software has the ability now to sort the meters based on this criteria, and I have this limit, which is currently set for 50 ohms. So depending on what mode I'm running here will depend how the sorting is done. The reason I'm using 50 ohms is our SEM meter that I have that has the RF link draws about 30 milliamps with a 9-volt battery. That meter will run down to about 8 volts before it conks out. So I said about 1.5 volts at 30 milliamps is 50 ohms. Certainly any higher than 50 ohms, it's definitely going to be a bad switch. Now keep in mind that most switch contacts are not used to actually power up the meter. And keep in mind that some meters, like our UT181 for example, have a MOSFET that actually turn on the power to the meter. So the current going through the switch is actually quite a bit lower. So it's really going to be meter dependent. In a lot of cases, the front end resistance of the meter is definitely going to be a lot higher than 50 ohms. It's going to be typically like 2K ohm or even in the megs. So in those cases, 50 ohms would be negligible. But certainly in cases where it is directly providing the power to the meter, or in some cases where they're switching in the shunt for the lower currents, that would definitely come into play because that now becomes part of the burden voltage. So in some cases you could probably get away with a higher resistance than 50 ohms. Again, it's kind of an arbitrary cut point. The BM869s draws roughly 5.26 milliamps, and it'll operate all the way down to about 6.5 volts. At roughly 6.4 volts is where the low battery indicator turns on. If we look for a 2 volt drop at 5.3 milliamps, that would give us roughly 380 ohms. With the backlight active, the meter draws roughly 30 milliamps. So again, with that 2 volt drop at 30 milliamps, that roughly is 66 ohms. And again, the worst contact resistance that I measured with the meter was roughly 1.3 ohms. So I doubt very much on this particular meter that the switch is the limiting factor of the life of the meter. So let's just go ahead and hit sort. And we can see the software picks the Fluke 17B Plus, followed by the Brymen, then the Agilent, Casuntes, eSun, and Baseline, and last is our Centec meter. So in this case, I can tell you that the Brymen BM869s never reaches 50 ohms. So let's just deselect some of these other meters. So this would be 50 ohms here, and you can see both those meters never reach that. Because neither of these meters met that criteria, the software can't distinguish which one is actually the better of the two meters. So again, if we select mean average, this is a rolling average of the last 50 samples. And again, the software is still going to look for this 50 ohm threshold, but it's looking at the average. So let's just look at the Centec meter, for example. If I had set this threshold for, say, 500 ohms, we could see this initial point didn't actually hit that. If I go to normal sampling, of course it does. So if a switch were just a glitch, for example, what this does is allows me to filter that out. So this may be a more realistic way of looking at how the switch is wearing. So when we select accumulated, we're still using the 50 ohm threshold, but now we're looking at the accumulated resistance, or when the total of all the samples reach that 50 ohm threshold. So in this case, you can see it basically reaches 50 ohms right at the start. Let's just zoom into the first few hundred samples. So right about here is where we hit 50 ohms, which would be roughly 100 cycles. If we look at our baseline meter, you can see it follows a similar trend. So when we're looking at accumulated, we probably want to pick the threshold that would include all the data sets, and we probably want to pick an area out here where there's actually a difference between the meters. So let's just set this for 10,000 ohms, and we'll resort. So again, we can see the Centec meter is on top, and that's followed by the eSun meter, which is violet, which is followed by our Agilent, and then the baseline meter, and then our Casun test, and then finally the Fluke and the Brymen meter at the bottom. You can see the profile for the Brymen and the Fluke are very similar. Let's go ahead and look at the log data. Again, this horizontal white line across the top denotes our 50,000 cycles. The red trace is our Fluke meter, and then this green trace is the Brymen. And then this purple line will be the Agilent, followed by our Casun test. Let's look at these in 3 dimensions. So this is looking at our Casun test meter. Notice the vertical scale is 0 to 1,000 ohms. And again, this will rescale depending on the meter that we're looking at. And again, the way that this works is we basically slice the data sets into segments. And in this case, each segment consists of 100 samples. So we're running 50,000 samples total. So if you take 500 slices times 100, gives you your 50,000 cycles total. We can see that this meter starts out quite flat, and then we can see it opens up fairly early on. This is looking at our baseline meter. Again, a similar bathtub curve where the meter starts out good, and then it opens up. That looks good for quite some time, and then you can see it opens up again. This is our Agilent meter. This is looking at the eSun meter. The Centec meter, again, it starts out actually pretty bad, and it just gets worse, and then we abort the test. Again, this is at roughly 17,000 cycles. Again, this is the Fluke meter, and notice again the vertical scaling is 0.35 to 0.37 ohms. This meter is by far the best one that I've looked at so far. And this is looking at the Brymen meter. Again, notice the scaling is 0.54 ohms up to 1.3. Let's zoom into the first couple of thousand cycles. Again, our tan trace here is the Centec meter, and you can see it's quite noisy. It gets all the way up to 38 ohms within about 1,500 cycles. The green trace is our eSun meter, and we can see it reaches 12 ohms at roughly 600 cycles. Let's just zoom in a little bit on the vertical axes. The violet trace is our baseline meter. Again, you can see it reaches roughly 2.1 ohms and slightly over 2,000 cycles. As we continue to zoom in the vertical axes, the yellow is the Casun test meter, and then the blue trace is the Keysight meter. The red is our Brymen, and then the white's the Fluke meter. Notice how flat this Fluke meter is compared with the others. Again, the Brymen meter starts to drift up. It actually looks quite flat. Let's just zoom out again to look at all 50,000 cycles. And then let's zoom into the vertical axis a little bit. So the red trace here is our Brymen meter. And again, we can see it about roughly 5,000 cycles. It gets a little noisy. And at 10,000 cycles is where we start to see the worst of it at roughly 1.3 ohms or so. And we can see it roughly maybe 13,000 cycles. Again, it starts to get quite quiet. See a little bit of noise out here at about 35,000 cycles. But again, look at the resistance of the switch at that point is 0.4 ohms. That's quite good. Again, this is our Casun test meter in yellow. And this is our Agilent meter in blue. And again, this is looking at the data as an average. So Brymen has stated that they've submitted the BM869s to UL. It has been certified for IP54. What that means is that it's basically splash proof in any orientation for water. And they also test this with a low pressure water jet. And again, that's in any orientation. See, I brought out a dead battery, and you can see the meter's reading roughly 3.5 volts. This thing will hardly make your tongue tingle. So I've got some string with me. This is a high test line. What I'm going to do is attach this around the meter, and then we'll take this thing down to the creek. Let's do a quick drop test of the meter first. This is probably about 15 feet down into the snow. See, the meter powers up just fine. You can hear the geese overhead. Set it to the ohm range. I think the water is semi-conductive. Alright, so looking at the lens, you can see how this thing is frosted over. Just for a quick check with our other Brymen meter, you can see that 9-volt battery was definitely dead. Again, they've stated that the meter was only rated for IP54. That certainly doesn't mean that the meter will work submerged in water. I just thought it'd be interesting to see how much water. Oh yeah, right there. So it picked up a fair amount. Wonder where that's coming through. If it's maybe on that front seal. You know, I did not take this meter all the way apart after we ran the 50,000 cycles. I wonder if maybe there's an O-ring where the knob mounts to that upper case. And if that's not where we're leaking, see, I got a little bit of snow packed down inside of this banana connector. See a little bit of water behind the shielding. I just find it hard to believe that it's leaking around these seals. If you ever decide to pull one of these apart, I just used a small piece of metal and wedge that in there and then just lift this tab back a little bit. See, a few stones got caught down into these cracks here. So let's go ahead and pop this C-clip. You can see a little bit of dust around the O-ring here. See up around the lip, just a little bit of dust. So I looked at the O-ring and it seems like this is in good condition. Once this were to stretch around the shaft, you can see it's a pretty good fit. See, I'm not sure if that's not where some of the water comes in, maybe at each one of these creases. It's kind of hard to say because there's nothing on the top that would help to seal that. So I've completely flushed out the LCD along with both circuit boards. Also ran a Q-tip down inside of each banana connector. So these are all cleaned out now. Everything should be set to go. So after I reassembled this, I took some rubber tubing, I slid it over the end of this, and I tried to draw a vacuum off of it. And it looks like this O-ring seals pretty good. So I don't think this is where the majority of the water comes in. What I'm going to do is push this thing underwater, and let's see if there's any air bubbles that escape. Yeah, it looks like it's actually sealed quite well. So you can see I buttoned the case back up. Of course, I've lifted the circuit boards out. Everything's tightened down. So I know it's not leaking through the rotary switch, the push buttons, or the lens. What I'm going to do is just flip this thing over, And we can see if we get any air bubbles out of this. Oh yeah. Right there out of the battery compartment. That's the only one. There's one more thing I'd like to mention before I close this video out. There's been some discussion about the lubrication and what to use on the switch contacts. Of course, I've used silicone grease on some of the meters that I have, but the thing I'd like to point out is the meters that are actually doing the best in these tests have all had dry contacts. So if we look at the 17B Plus, for example, that was a dry contact meter. Of course, this Brymen BM869s uses dry contacts. So I would not necessarily assume that adding grease to a contact is going to make it last longer. The only thing that I've seen come up occasionally is people will post how some of the meters that I've ran that have passed at such high voltages do so because of the grease that's on the contacts. Again, this Brymen and the 17B Plus did quite well in the transient testing, and again, they don't have grease. Some of the meters that have done quite poorly have actually had grease. So I'd just like to point out that just because a meter has grease on the contacts doesn't mean that it's going to do well on my testing. And meters that don't have grease aren't necessarily going to do poorly as well. So I'd like to take this time to thank Brymen for sending me this BM869s. Hopefully running these tests helped give us some indication on how the meter was going to perform in the long term. Personally, it looks like to me that if the meter were to have a short life, it's probably not going to be due to the switch failing. It also looks like we have a few new followers. I'd like to take this time to welcome you as well. I'd like to wish everyone a Happy New Year until the next test. Later.